Alright guys, so we're diving into 3.9, which is find the derivatives of exponential and log functions. So we previously have just finished up finding the derivatives of inverse trig functions. And now we've got some goals in 3.9 in which we're trying to make sure that we find the derivatives of different types of exponential function, different types of logarithmic function. So by this is all said and done, we want to make sure that you guys can actually find the derivatives of functions that look like e to the x, derivative functions that look like some value for a to the x power. We want to find derivatives of functions using the natural log, and then finding derivatives of functions using log with a random base of a. And that's going to be kind of split up between two parts between this goal. And so for our purposes in this video, we are going to look into part one, which is find the derivatives of e to the x and a to the x. And so let's start off by saying recap, right? So if you kind of remember back to dealing with the pre-calculus days, we talked about the function y equals e to the x, okay? So let me just put it off to the side here. Y equals e to the x. And the function y equals e to the x is an extremely important function, and mostly because we dealt with it, hopefully if you remember correctly, with exponential growth, right? So we showed it usually with exponential growth. And then we looked a few times into the limits. Hope you remember our limit days as well too. That we said as the limit of x approaches infinity of this particular function, we left off with, let me put this over here for the side. The limit as x approaches infinity of the particular function, we ended up finding this out to be 1 plus 1 over x all to the quantity of x, okay? In this case, you know, does this happen right now? No, but it's important to know, and so I'm going to geek out on you a little bit here, and just bear with me as to where I'm going with this, okay? So the function e to the x is an extremely important function, and it's probably most important is about to happen right now, okay? So listen, hang in there as I geek out a little bit and go through a little bit of things. So I have something here in green. I say suppose the limit as h approaches 0 of e to the h minus 1 over h equals 1. And actually, don't really suppose it. Just take it for my word that this actually is the case. All right, we can solve it on out if we really wanted to, but that's not our goal for this. But the limit of this function does, in fact, equal 1. And so why is this really that important to us? To you at the moment, not a whole lot. But we're about to find out that because this limit equals 1, it creates a very, very, very interesting relationship between the function e to the x and its derivative. So let me highlight this once again. Keep in mind that the limit of this particular function equals 1 as h approaches 0. Because for what we're going to look into right now is we're going to basically prove why the derivative of e to the x is what it is. And maybe because this equals 1, before I go into it, take a quick guess to yourself. What do you think the derivative of e to the x is going to be if this is going to equal 1? Hint, hint, wink, wink. Let's dive right in. So let's say, for instance, I want to find the derivative of e to the x. As of right now, we don't know it, okay? We don't know what derivative of e to the x is. Now, if you're watching this for, a second time or two, you know what it is. But let's do it the old way. Remember, we know how to find the derivatives using limits. And let's use limits for a sec, hence why I gave you the suppose up top. Let's use limits to find what's happening here with our derivative of e to the x. So we know the derivative of e to the x is the limit as h approaches 0 of e to the x plus h, that's whatever the change in x was, minus the original function e to the x over the change in h, all right? Well, it's h minus 0, right? There's h minus 0 that just becomes h. And so really that's all I'm looking at in this particular instance. And so let's find the limit of this function and see what happens here, because this is what the derivative is going to show us when it's all said and done. Well, let's take a look here. The limit as h approaches 0 of this numerator. We all agree that e to the x plus h is the same thing as e to the x times e to the h, right? It's the exact same thing. So by doing so, why is it important to us? Because remember, when it comes to limits, we want to cancel things out and utilize things we know. We just were told that the limit as h approaches 0 of e to the h minus 1 over h equals 1. Maybe we can use this to our advantage in the limit below. So e to the x times e to the h minus e to the x, all in the numerator. What do you notice is on top? I notice that there's an e to the x in both of the the monomials that we're dealing with in this particular example. And so I'm going to factor out e to the x in this example. So I can take out, by our limit rules, limit as h approaches 0, multiply it by e to the x, and now I'm left with e to the h minus 1 over h. Well, looky there, folks. This looks pretty familiar to what we just were told, that the limit as h approaches 0 of e to the h minus 1 over h equals 1. Why is this important to us? Well, look what's about to happen. If this limit equals 1, this is e to the x times 1. Well, we know this is e to the x. So think about what just happened. My question to you is, what is the derivative of e to the x? Hopefully, we now understand that the derivative of ex is equal to e to the x as well. Okay? So that's why it's a really interesting kind of limit that we're dealing with up top, and why it's so important to think about limits in terms of derivatives and don't just let it go by the wayside for what we're dealing with here. So when it's all said and done, our kind of rule that we use for derivatives, if I want to find the derivative of e to some function, right, to some function using x's and y's or whatever the case is, but in this case, if it's derivative with respect to x of e to the u, where u is, x squared, square root of x, whatever the case could be, we take the derivative of itself times whatever is inside that u part of the function. So the derivative of whatever u actually is. So before we get out of here, let's do one more formula. Keep this in your back pocket, extremely important to know. And that also kind of leads us into our other one as well. Now, I won't bore you with my geek out side of things to find a to the u, but let's say, for instance, we want to find the derivative of a to the u. So now the exponential function, now it's just a random number being raised to some variables that are in there. And so in this case, it's pretty darn similar, but because we're not using e, we have to incorporate its inverse natural log. And so we take a to the u and ln of a, multiplying by whatever the derivative, you guessed it, of u is as well. So these are our two big take-homes for today's lesson. Finding the derivative of u and find the derivative of a to the u. So let's go and take a quick example of using our e to the u derivative formula that we just looked into. So let's say, for instance, we are dealing with the example in which we want to find dy dx if y equals e to the x plus x squared power. Well, we know the derivative in this case is going to be e to the u times the derivative of du dx. So we have to identify what u is going to be. Well, I know this is u substitution at its finest right here. This is our chain rule being used all in one. So let's go ahead and make u into that upper part, that exponent, x plus x squared. And let's just make y equaling e to the u. Again, why is important? Because this is going to allow us to basically use this formula right here. So let's find the derivative. Let's find du dx. So du dx in this case is going to be 1 plus 2x. And I know du dx is going to be 1 plus 2x now. So now I just take e to the u times du dx. Well, e to the u is really e to the x plus x squared power being multiplied all by 1 plus 2x. And there is our derivative in this particular example. All right. So I want you guys to do is I want you to give one a shot on your own before we wrap things on up. So your example to give a shot on your own is y equals e to the square root of x. Find dy dx. And I will reveal the answer to you in this example is going to be e multiplied by the square root of x over 2 multiplied by the square root of x. I guess you could probably make this a little bit easier for you. Hold on, sorry guys. Let me make this a little bit clearer because that doesn't look quite as clear. E times the square root of x over 2 times the square root of x. See if you come up with that same result, and we'll talk about it on our next video.